Oui, donc on va continuer. Est-ce que Katharina est en ligne? Merci. Katharina, do you hear me?
Yes, I hear you.
So I make a short introduction in French and then you can speak. Katharina Kreuzel, c'est une jeune chercheuse et remarquable chercheuse qui travaille à l'Institut de Visual Computing on Human Centered Technology. Et donc, elle est membre fondateur de la section autrichienne de l'IEEE, le site que nous avions vu déjà. Et elle est auteure de nombreux articles scientifiques. Et son sujet, c'est la simulation de la cataracte en réalité virtuelle. Donc, simulation of cataract in virtual reality. Please, Katharina, you can talk.
Thank you. Thank you for the introduction. So, hello, everyone. Also, for the English-speaking audience, my name is Katharina Kreuzel. I'm a postdoctoral researcher at the VIAVIS Research Center in Vienna. And it is my pleasure to present our work on simulating cataracts in virtual reality here today. This is an image of a typical escape route sign. It shows the shortest path out of a building in case of an emergency. Such signs have to be installed in a certain maximum distance to the next sign, so people have always one sign in sight that they can read. But what if you have some form of visual impairment that makes it harder or almost impossible to recognize the direction on the sign? This is a common problem for a lot of people. At least 2.2 billion people worldwide are affected by vision impairments or blindness, according to the World Health Organization. This number is expected to increase due to different factors, such as aging of the population. This is because many eye conditions, as you will know, show a higher prevalence with age. So we have a large number of people with vision impairments that we should take into account when we design our cities, buildings, lighting systems, or signage. To create an inclusive society, we need to increase awareness and empathy for people with vision impairments and the challenges they face in their everyday lives. However, taking vision impairments into account in architecture or lighting design is quite difficult because architects and designers lack the tools and the methodology to properly evaluate their designs for accessibility. So they need a way to really understand the impact of vision impairments on perception and what that means for their designs. To train medical personnel, we have to use textual descriptions or 2D images in books to explain how a certain vision impairment affects the eyesight of a person. So wouldn't it be better if medical students, architects, or relatives of people with vision impairments could experience firsthand how the world looks like if your eyesight is affected by some vision impairment or eye disease? Well, this is why we need vision impairment simulations. Some researchers used physical goggles with special lenses or foils to create the effect of different eye diseases. Real goggles might be suitable for educational purposes, but each pair is limited to simulate one particular vision impairment. So you cannot adjust the severity of symptoms other than using a different pair of goggles or swapping the lenses. They are also not adjustable to the vision capabilities of users. So a person who is already a little bit short-sighted will have a slightly different experience as a person with a normal sight when using these goggles. An approach that is used a lot to show people the effects of vision impairments is to modify 2D images. This has been used in various works on simulating color vision deficiencies and also in web design in order to let designers test their websites for accessibility. These images of vision impairments provided by the National Eye Institute of North America inform a lot of research in this area. However, the obvious disadvantages of 2D images are that they are not immersive. They are still images. They are not adjustable for individual users and can simulate gaze-dependent effects, but many vision impairments affect different areas of the visual field differently. And so it depends where a person is looking at. This means we need something better, closer to reality, something more immersive. And this is where virtual reality comes in. You put on a head-worn display and see a stereoscopic view of a virtual computer-generated world. There's a whole body of research on simulating vision impairments in VR with different limitations. Many simulations are just simplified depictions of eye diseases and do not combine multiple symptoms to simulate complex eye disease patterns. Only very few simulations use eye tracking to simulate gaze-dependent effects, something that is really crucial if you want to create a realistic simulation of a vision impairment that affects different areas of your field of view differently. And to the best of our knowledge, no other work on simulating vision impairment takes hardware limitations and vision capabilities of users into account. And this is important because the resolution of a display, for example, or the short-sightedness of a person could impact their perception inside the head-worn display, and therefore create a different experience for them when using the VR simulation. But if we want our simulation to look exactly the same for different users, we have to take this into account. So if we summarize the limitations of prior work, we can identify the following requirements for vision impairment simulations. We have seen that hardware goggles or 2D images cannot provide an immersive simulation. However, this is vital if we want to understand how a person with a vision impairment perceives the world. Eye diseases are a combination of different symptoms, the different severity. So therefore, it is important that we can adjust each symptom individually and combine multiple symptoms to create simulations of complex eye disease patterns with gaze-dependent effects. If we want to use these simulations for user studies with healthy subjects, we need to make sure that our simulation is perceived similar by every user. Only then do we get meaningful results from statistical evaluations. So our final goal here is to create realistic, medically informed simulations of eye diseases that can be used to raise awareness, train medical personnel, and help us understand the impacts of vision impairments on perception better, and also help architects and designers to test their designs for accessibility. The World Health Organization identified cataracts as one of the leading causes for vision impairments. Therefore, we picked cataracts as our first target and created a cataract simulation. As you will know, cataracts are opacities in the lens of the eye, which occlude parts of the visual field and can also lead to vision loss when left untreated. Depending on their characteristics and the region of the lens that is affected, cataracts are categorized as nuclear, cortical, or posterior subcapsular cataracts. The literature lists different symptoms caused by cataracts, such as cloudy or blurry vision, faded colors, tinted vision, trouble seeing at night, increased sensitivity to light, halos around lights, or double vision. We worked with ophthalmologists and concentrated on the most common cataract systems and developed an effects pipeline to simulate cataracts in virtual reality with this head-worn display and HTC Vive Pro, using eye tracking for gaze-dependent effects. This is the virtual environment we used for our experiments. We calculated a physically plausible lighting simulation for this kitchen model using the light planning software Highlight, which is developed at the VIVIS Research Center. We simulate 3 different types of cataracts: nuclear cataracts, cortical cataracts, and posterior subcapsular cataracts. So in order to do this, we combine different effects to simulate these cataract disease patterns. First, we reduce the visual acuity of a user using a depth of field effect, which basically means that the severity of the blurring that you experience in different regions of the image depends on the distance to the objects that are in your field of view. For example, nearsighted people can see objects that are very close to their eyes sharply, while everything in the distance appears blurred. And the applied effect leads to this blurred vision. We determine the amount of blur we need by implementing an eyesight test in VR. So everyone here probably is familiar with this, but to establish the basics for this talk, I will briefly talk about how we measure visual acuity. A common test distance are 6 meters or 20 feet. A person with normal sight should be able to recognize a small detail like the gap in this Landolt sea of approximately 1.75 millimeters in size at 6 meter distance. So this corresponds to a viewing angle of 1 arc minute. If the smallest detail a person recognizes at 6 meter viewing distance is larger than that, for example, 2 arc minutes, so twice the size, it means that the visual acuity of this person is half as good. So this person can recognize details that are double in size or the same size at half the distance. Normal vision is usually called 6.6 or 20/20 vision or 1.0 decimal acuity. So decimal acuity is calculated as the distance at which the test subject can recognize a small detail divided by the distance at which a person with normal sight would be able to recognize the same small detail. So if my visual acuity is just half as good and I recognize a small detail of 1.75 millimeters or 1 arc minute only from 3 meter distance, I have 0.5 decimal acuity. This means we can calculate which size of small details a person with a certain visual acuity can recognize at a certain test distance. And this is important for our approach. We simulate a reduced visual acuity by applying a Gaussian blur to the image. So we know which size of Landolt sea a person with a certain visual acuity can or cannot recognize anymore. In a normal eyesight test, you would start with a large Landolt sea and stepwise decrease the size to find the visual acuity of the test subject. Here you can see a visual acuity test in VR. The user sees a Landolt sea in the distance and a small Landolt sea above the controller. By moving the thumb on the trackpad of the controller, the user can turn the Landolt sea above the controller to match the orientation of the one in the distance. If they match, the distant Landolt sea becomes smaller. To reduce the visual acuity for our simulation, we do not make the distant Landolt sea smaller. We start with a size and a distance that corresponds to a certain visual acuity and keep the size and distance fixed. Then we apply our blur to the image and stepwise increase the blur until a user is not able to recognize the gap in the Landolt sea anymore. Then we have calibrated the vision of this user to the predefined level of reduced visual acuity. Next, we reduce the contrast. We can use the same methodology to reduce contrast as for visual acuity. Only this time, instead of stepwise blurring the image, we stepwise reduce the contrast. And we are therefore able to simulate a similar amount of contrast loss for all users. We follow the protocol of the Pelly-Robson contrast sensitivity test, but use Landolt seas instead of the letters like on the Pelly-Robson chart. Next, we apply a color shift, which creates this yellowish vision. And then we simulate these dark shadows of a clouded lens typical for posterior subcapsular cataracts, which will be scaled according to the pupil size of the user. In the final step of our effects pipeline, we simulate sensitivity to light by using a Bloom effect, like you can see here in the upper left corner of the image. So image sources that create bright lights will create these glaring effects. And here you can see a video of this simulation. Whenever the user looks into a bright light, this glaring effect appears. And here we have a simulation of dark shadows typical for cortical cataracts, where you experience dark shadows in your periphery. So this means if I look at something very, very dark, my pupil gets wider and more of these dark shadows appear. We also used our simulation to run a user study and investigate maximum recognition distances of escape route signs with different vision impairments. We further modified the simulation for the use in video see-through augmented reality, where you don't see a virtual computer-generated world around you. You see your real environment as it is recorded by the front-facing cameras of the head-one display. And we also added more simulations of different vision impairments and conducted a pilot study with cataract patients to adjust our simulation to their vision with cataracts. This allows us to simulate the actual cataract vision of these patients more truthfully than ever before, and let others with normal sight experience this vision and become aware of the problems and challenges people with this impaired vision face in their everyday lives. And with this, I want to thank you for your attention.
Catalina.